Good day, everyone. So for today is lesson 8. It's about analysis, interpretation, and use of test data. So the desired significant learning outcomes. So in this lesson, you are expected to analyze, of course, to interpret and use the test data by applying the following, such as the measure of central tendency, B. Measures of variability, C. Measures of position, and D. Measures of convariability. So the prerequisite of this lesson. So in this lesson, the discussions is we will build upon the concept and example presented in lesson 7. So which it focused on the tabular and graphical presentation and interpretation of test results. So in this lesson, other way of summarizing the test data using descriptive statistics, it provides a more precise and of course it describes a set of scores will be discussed. So the word measures, it commonly used or associated with numerical and quantitative data. So henceforth, the prerequisite to understand the concept contained in this lesson is your basic knowledge of mathematics, such as summations of values, simple operations on integers, squaring and finding their roots, and etc. etc. So means, what are the measures of central tendency? So first off is means. So the central location or point of convergence of a set values. And second, it provides us a test scores to have a tendency to converge at a central value. And by doing so, it can provide us a value in the average of the set of scores. And it can provide us a 3 commonly used measures of central tendency, of measures of central locations, such as mean, median, and of course, mode. So mean. So mean is most preferred measures of central tendency for the use of test scores, and can also referred as an arithmetic means, and can computate is and its computation is very simple. As I've seen in my screen is one of the examples of its computations. So consider again the test scores of student given in table 8.1, which is the same set of test scores of the previous lesson. So as I've shown you in the screens, these are the test scores that the 100 college students has given in the final examinations. So the mean is to sum up all the scores from 53 down to the last scores, which is 35. And furthermore, frequency distribution of group test scores. So first off is the class interval, which is the 75-80, and the midpoint is 77. By midpoint, it's the midpoint between 75 and 80. And the frequency of 75 and 80 is 3, obviously, since the midpoint of 75 and 80 is 77. And we have XIF, which is 231, and cumulative frequency, or for short CF, which is 100, or cumulative percentage is also 100. Okay, let's move on to the next one. In the traditional way, it cannot be argued that you can see at a glance on how the scores are distributed among the range of value in a condensed manner. So you can also estimate the average of the scores by looking at the frequency in each class interval, such as this, as I've explained later on, which is 75, 80, 70, 74, which is the class interval 65, 69. So let's move further on. So distributed among the range of value in the condensed manner. So you can also estimate the average scores by looking at the frequency in each class interval. So in the absence of statistical program, the mean, such as MEAN, can be a computer by the following formula. This one. So where x1, or midpoint of the class interval, f stands for the frequency of class interval, and n is total frequency. Thus, the mean on the test scores in the table 7.1 is calculated as follow. That one. So let's move on with the report. So median. So median is the value that divides the ranked score into halves, or the middle value of the ranked score. The second one, if the number of scores is odd, then there is only one middle value that gives you the median. However, if the number of scores in the set is an even number, then there are two middle values, such as the frequency distributing of group test scores. This one. So this formula can also help you determine the median. MDN, or lower limit size of the class intervals of medium class. So let's move on. Mode. So the easiest measure of central tendency to obtain, it is the score or value with the highest frequency in the set of scores. If the scores are arranged in a frequency distribution, the mode is estimated as the midpoint of the class interval, which has the highest frequency, as I've shown you in the last part, such as this one, for example. So to appreciate comparison of the three measures of the central tendency, a brief background of a level of measurement is important. And by that, the level of measurement helps you decide how to interpret the data as measures of attributes, and this serves as the guide in determining in the part the kind of descriptive statistics. It can also apply in analyzing the test data. So from my last report, it's about the scale measurements. So there are levels of measurement that apply to the treatment of tests, such as nominal, ordinal, interval, and ratio. But this is where I'm gonna stop, and my group mates will further explain the report, so forth. Thank you.
So good morning everyone. I am the second reporter of Group 8. I am Karen Cafe, so we'll start now. So my topic is all about what are measures of dispersion. So measures of dispersion, which indicates the variability, spread or scatter. Measures of dispersion describe the spread of the data to include the range, interquartile range, standard deviation, and variance. So there are several indices of variability, and the most commonly used in the area assessment in the range, variance, and standard. So here is the figure 8.4 measures of variability of the sets of test score. So indices of variability in range is the difference between the highest scores and the lowest of a distribution. So this example, we can determine the range, and the range is the highest score minus the lowest score. So here is the highest score is the 20. So, and the lowest score is 9. So, 20 minus 9 is equal to 11. Now, replace a high score in one of the score. Say that the last score, make it 50. So, the range becomes, so range is equal to highest score minus lowest score. So the highest score is 50. 50 minus the lowest is 9. So the equals is 41. So the answer is 41. 50 minus 9 is equal to 41. Variance and the standard deviation. The most widely used measure of variability and considered most accurate to represent the divisions of individual score mean values in the distribution. So here are the tables or the examine following score distribution. So these tables include the score distribution. So the class A, here are the class A, class B, and the class C. So EX means, ano na EX is, muna siya gipasabot o ka ng sigma. Sigma and the X is stand for the row score or score in a distribution. So sigma row score is equal to 120 and X nga naitagli sa taas is the mean score or X bar. So sigma row score is equal to 120, then mean score is equal to 120 divided by 10 is equal to 12. So the same with the class B and the class C. Muna siya score distribution sa variance and standard division. So dirita sa variance and standard deviation. The measure is generally defined by the formula. So here are the formula. Ni siya kaning numeric 0 na 0 squared mo ni siya kitawag og population standard deviation symbol. So population standard deviation symbol is equal to sigma. Ang X stands for the value in the data distribution minus squared. So population standard deviation symbol is equal to sigma population standard deviation symbol is equal to sigma times the value in the data distribution. So the X stands for the value in the data distribution times squared divided by N. So N stands for the population mean. So where population standard deviation symbol is equals to population variance. So kani siyang the formula is kanimo N population mean and the X is score in the distribution or the value of data distribution. Finding the square give us this formula for the standard deviation. So that is the popular distribution symbol, square root of sigma times the value in the data distribution minus population mean squared divided by the population mean. So the N, diba? The N is population mean. So again, population standard deviation symbol, square root of sigma times the value in the data distribution minus the population mean times square divided by the population mean. So muna siya pagpasaan niya sa formula. So where population standard deviation, population mean o score in distribution. So variance and standard deviation, if we are dealing with the sample data and wish to calculation and S, the following formula is used to such statistics. So ang S, example sa S, ang S stands for sample standard deviation symbol. So sample standard deviation symbol. Sample standard deviation symbol, square root of sigma sigma and the value in the data distribution minus x squared times the population mean over the population mean. Ay kanina yung x nga na-icon sa taas mean score. So again, S is sample standard deviation. Sample standard deviation is equal to square root of sigma times the value in the data distribution minus mean score times the number of score in distribution divided by the number of scores in the distribution. So the value of 276 and 74 are the sum of the squared divisions of scores in class A and class B, respectively. If there are divided by number of scores in each class, this gives the variance sample distribution standard symbol squared. So here again, here is S squared is equal to 276 divided by 10 minus 1 is equal to 30.67, and there's a pika 74. Ang 74 is the sum na siya sa square division sa class A o class B. Itong ganinang class A o class B. So, S squared is equal to 74 divided by 10 minus 1. Answer is 8.22. So, hindi ko nasa yatag siya, given na siya ang 276 o kuan 74. So, guys.
So, the measures of central tendency and the measures of dispersion is already done. And now, let's proceed to the measures of position. So, what are the measures of position? So, while measures of central tendency and measures of dispersion are used often in assessment, there are other methods of describing data distribution, such as using measures of position or location. So what are these measures? We have the quartile, decile, and percentile. First, let's talk about the quartile. The quartiles are the three values that divide a set scores into 4 equal parts, with 1/4 of the data values in each part. Quartiles are also used as a measure of the spread of data in the interquartile range, or the IQR, which is simply the difference between the third and the first quartiles, Q third minus Q1, or the first quartile and the third quartile. Half of this gives the semi-interquartile range, or quartile deviation, or Q. The following examples illustrate the above mentioned measures. So here is the example. So given the following scores, find the first quartile, third quartile, and quartile deviation. So we have 90, 85, 85, 86, 100, 105, 109, 110, 88, 105, 100, 112. So there are the following steps to be followed in finding the first quartile, third quartile, and the quartile deviation. So the first one, we have arrange the scores in the decreasing order steps. Decreasing order means that you need to start to the highest level, or to the highest number, till to the lowest number. So the second one, from the bottom, find the points below which 25% of the score value and 75% of the score values fall. Third, find the average of the two scores in each of these points to determine first quartile, or Q1, and third quartile, Q3, respectively. And fourth, we need to find Q, or the quartile deviation, using the formula Q is equals Q third minus Q1 over 2. So, applying these steps in the above example, we have the upper half and the lower half. So the lower half includes all data below the median, while the upper half includes all data above the median. And in calculating the third quartile, the upper half we have 112, 110, 109, 105, 105, 109. So in calculating the third quartile, we have the third quartile here is 109 and 105. Over 2 is equals 107. So 107, it is the median calculated as the average of the two middle values, which is the 109 and 105. So while the lower half we have 190, 88, 85, 86, 85. So the first quartile we have 88, 86 over 2 is equals 87. So 87 is the median calculated as the average of the two middle values of 88 and 86. So note that in the above example, the upper and lower 50% contains even center values. So the median in each half is the average of the two center values. So consequently, in applying the formula, Q third or the third quartile minus first quartile, or Q1 over 2, gives the quartile deviation. So that is Q is equals 107 minus 87 over 2 is equals 10. So why is it the answer is equals 10? So we have 107 minus 87 is equals 20. So 20 and 20 we are going to divide it by 2. So 20 divided by 2 is equals 10. So the value of quartile deviation is 10. The next one we have the decile. So the decile, it divides the distribution into 10 equal parts. There are 9 deciles such that 10% of the distribution are equal or less than decile 1 or D1. 20% of the scores are equal or less than decile 2 or D2, and so on. A student whose mark is between the first and second deciles is in decile 2, and one those mark is above the 9 decile belongs to the decile 10. If there are small numbers of data values, decile is not appropriate to use. So it means that deciles divide a data set into 10 equal parts, with each containing 10% of data points when arranged in ascending order. So ascending order means arranging numbers or data from the smallest to the largest number. So each decile corresponds to the specific percentage. So the decile 1 is the bottom of 10% of the data, and the decile 2 is the bottom 20% of the data, and so on. Well, and the decile 10 is represents as the top 10% of the data. So if a students fall into decile 2, it means their score is higher than the bottom 10% but lower than the top 80%. If a score is in decile 9, it belongs to the top 20% but below the top 10%. So if the decile is have a small numbers of the data values, it is not appropriate to use. And next we have the percentile. So it divides the distribution into 100, equal parts. In the same manner, for percentiles, there are 99 percentiles such that 1% of the scores are less than the first percentile, 2% of the scores are less than the second percentile, and so on. For example, if you scored 95 in a 100-item test and your percentile rank is 99, then this means that 99% of those who took the test performed lower than you. This also means that you belong to the top 1% of those who took the test. In many cases, percentiles are wrongly interpreted as percentage score. So, for example, 75% as a percentage scores means you get 75 items correct out of 100 items, which is a mark of grade reflecting performance level. But percentile is a measure of position such that 75th percentile as your mark means that 75% of the students who took the test got lower score than you. Or your score is located at the upper 25% of the class who took the same test. For a very large data set, percentile is appropriate to use for accuracy. This is one reason why percentiles are commonly used in national assessments or university entrance examinations with large data set or scores in thousands. So let's proceed to the coefficient of variation as a measure of relative dispersion. So what is the coefficient of variation as a measure of relative dispersion? So we need a measure of relative dispersion which dimensionless or unit-free. This measure of relative dispersion is also known as coefficient of variation. So this is simply the ratio of the standard deviation of a distribution and the mean of distribution. So CV means the coefficient of variation is equals to the standard deviation of the data, which measures how much the data values vary around the mean, over the mean or the average of the data representing the central tendency of the data set, multiplied by 100. It is used to express the coefficient of variation as a percentage. So the above formula indicates that coefficient of variation is a percentage value. Thus, if the mean score of the students in mathematics is 40 with a standard deviation of 10, then the coefficient of variation is computed as. So we have here the students in mathematics is 40, so the coefficient variation is equals 10, which is the standard deviation, over 40, the score of the students in mathematics, multiplied by 100 is equals 0.25. So if we are going to make it as a percent, it is 0.25 is equivalent to 25%. Suppose the mean score of students in science is 18 with standard deviation of 5. The coefficient of variation is equals 5, which is the standard deviation, over the score of the students in science 18 multiplied by 100 is equals 0.227. When we are going to transform it into percentage, we have 28%. So from the computed coefficient of variations as measure of relative dispersion, we can clearly see that the scores in mathematics are more homogeneous than the scores in science. So let's proceed to the coefficient of variation. So how to find a coefficient of variation? So we have here the example that given. So example questions. Two versions of a test are given to students. One test has preset answers, while the other one is, or the second test has randomized answers. So we have here the regular test and the randomized test. The mean is 50.1, this is 11.2, and 45.8, 12.9. So we have here the following steps to find on how we are going to find coefficient of variation. So step 1, divide the standard deviation by the mean from the first sample. So the first sample we have 11.2 over 50.1 is equals 0.22355. Step 2, multiply step 1 by 100. Okay, so the answer by step 1 is equals to 0.22355 multiplied by 100 is equals to 22.355%. Step 3, divide the standard deviation by the mean for the second sample. So we are going to divide the standard deviation by the mean for the second sample. We have the 12.9 divided by 45.8 is equals to 0.28,166. Step 4, multiply step 3 by 100. So the answer on the step 3, we are going to multiply it by 100. So 0.28,166 multiplied by 100 is equals 28.266%. So next, we have the standard deviation applied in a normal distribution. So how is standard deviation applied in a normal distribution? Let's find out. The standard deviation is viewed as the most useful measure of variability because in many distributions of scores, not only in assessment but in research as well, it approximates the percentage of scores that lie within 1, 2, or 3 standard deviation from the mean. So the normal distribution, special kind of symmetrical distribution that is most frequent used to compare scores, are drawn as a smooth curve. One curve stands out, which is the bell-shaped curve. It is also called Gaussian distribution, named after Carl Friedrich Gauss. The standard deviation is used to determine the percentage of scores that fall within a certain number of standard deviations from the mean. So let's take a look from the figure 8.6, the normal curve. So in assessment, the area in the curve refers to the number of scores that fall within a specific standard deviation from the mean score. In other words, each portion under the curve contains a fixed percentage of cases as follows. So the first, we have 68% of the scores fall between one standard deviation below and above the mean, and 95% of the scores fall between two standards deviation below and above the mean. And the last one, we have the 99.77% of the scores fall between three standard deviations below and above the mean. So the following figure further illustrates the theoretical model. We have here the figure 8.7, which is the area under the normal curve. So that figure, it is the areas under the normal curve. So from the above figure, we can state the properties of the normal distribution. So we have the mean, median, and the mode are all equal. So the curve is symmetrical as such. The second is the curve is symmetrical as such. The value in a specific area on the left is equal to the value of its corresponding area on the right. Third, the curve changes from concave to convex and approaches the x-axis, but the tails do not touch the horizontal axis. Fourth one, we have the total area on the curve is equal to 1. So let's proceed to the standard scores. So what are the standard scores? So according to study.com, standard score is a set of scores that have the same mean and standard deviation so they can be compared. The most useful is the z-score, which is often used to express a row score in relation to the mean and standard deviation. This relationship is expressed in the following formula. Z is equals x minus x over 1 over x is. Recall that x minus x is a deviation score. So the x minus x, it is a deviation score. With this difference, you're able to know whether your test score, say x, is above or below average score. The standard deviation helps you locate the relative position of the score in a distribution. So a z-score is called a standard score. So it means that a z-score is a standard score. So simply because it is a deviation score expressed in standard deviation units. If row score are expressed as z-score or the standard score, we can see the relative position in the respective distribution. Moreover, if the row score are already converted into standard scores, we can now compare the two scores even when these scores comes from different distributions or when scores are measuring two different things. So let us take a look in the figure 8.8. It is a comparison of score distributions with the different means and standard deviation. So in the figure, a score of 86 in English indicates better performance than a score of 90 in physics. Let us suppose that the standard deviations in English and physics are 3 and 2 respectively. So ZE, or the standard score, is equals 86 minus 80 English, we have here the English score is 86 minus 80 over 3. So it is equals to, well, the standard score in physics, we have 90 minus 95 over 2 is equals to negative 2.5. So the English score Z is equals to is indicates better performance as it is well above the mean. While the physics score Z is equals negative 2.5 indicates weaker performance as it is significantly below the mean. So from the above, if 86 and 90 are your scores in two subjects, you can in English say that compared with the rest of your class, you perform better in English than in physics. That is because in English, your performance is 2 standard deviations above the mean. While 90 is numerically higher, this score is more than half standard deviation below the average performance of the class where you belong, while 86 is above the mean and even 2 standard deviations above it. So what are standard scores? We have here the figure 8.9. Different raw scores in one z-score distribution. Note that in figure 8.8, the shaded area in two graphs, here the shaded area in two graphs, it indicates the proportion of scores below yours. This is the same as saying that this portion is the number of students in your class who scored lower than you. So, examining the area under the normal curve, we can say that about 98% in your class scored below you in English, while the 1.2% scored below you in physics. We assume here that the scores are normally distributed. Now we have the t-score. As you can see in the computation of the z-score, it can give you a negative number, which simply means the score is below the mean. However, communicating negative z-score as below as the mean may not be understandable to others. So one option is to convert a z-score into a t-score, which is transformed standard score. So the t-score is a transformed standard score. There is a scaling in which a mean of 0 is a z-score is transformed into a mean of 50, and the standard deviation in z-score is multiplied by 10. The corresponding equation is here given. T-score is equals 50 plus 10z. For example, a z-score of negative 2 is equivalent to a t-score of 30, that is t-score equals 50 plus 2 multiplied by negative 2. So it is equals, copy sang 50, 10 divided by negative 2 is equals minus 20. So negative 20. So 50 minus 20 is equals 30. So how come 10 A positive 10 multiplied by negative 2 is equals to negative 20. So when we are going to multiply, we are going to copy the sign or the negative sign of the negative 2, which is the positive 10 multiplied by negative 2 is equals negative 20. So it is equals 50 minus 20 is equals 30. Easy as that. So looking back at the English score of 86, which resulted in a z-score of 2 as shown in the figure 8.7. The figure 8.7. Looking back at the figure 8.7. So we have here this one, the areas under the normal curve. Okay, so proceed to the standard or so. Looking back at the English score of 86, which resulted in a z-score of 2 as shown in the figure 8.7, t-score equivalent is equals 50 plus 10 multiplied by 2 is equals 50 plus 10 multiplied by 2 is equals 20. So 50 plus 20 is equals 70. So it is much more understandable than the z-score. So now let's proceed to stanine scores. Another standard score is a stanine, shortened from standard 9. So stanine is a shortened form of standard 9. So with 9 in its name, the scores are on a 9-point scale. In a z-score distribution, the mean is 0 and the standard deviation is 1. In this scale, the mean is 5 and the standard deviation is 2. Each stanine is 1/2 standard deviation wide. Like the t-score, stanine score can be calculated from the z-score by multiplying the z-score by 2 and adding 5. So we have here the formula. Stanine is equals 2z or the z-score plus 5. So going back to our example on a score of 86 in English that is equivalent to a z-score of 2. Its stanine equivalent is stanine is equals to, here we are going to use this formula, the stanine, the last one. Okay, the stanine 2z, the value of z is equal, or the z-score is 2 plus 9 is equal, plus 5 rather is equals 9. So how come it is equal to 9? So 2 multiplied by 2 is equals 4, add by 5 is equals to 9. So example, scores in stanine scale have some limitations since they are a 9-point scale and expressed as a whole number, they are not precise. So we have here the table, the z-score, t-score, and stanine. So in z-score, we have 2.1, 2.0, 1.9. The t-score, we have 71, 72, 79. And the stanine, 999 or the triple 9. So on the assumptions that stanine scores are normally distributed, the percentage of each cases in each band or range of scores in the scales as follows. So we have here the stanine scores. Let's take a look at the table. The Okay, so we have the Stanine score and the percentage of scores. So Stanine score, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. At the percentage of scores, lowest 4%, next low percent 77%, third next slow 12%, fourth next slow 17%, fifth middle 20%, sixth next high 17%, seventh next high 12%, eighth next high 7%, and lastly ninth highest of 4%. So with the above percentage distribution of scores in each Stanine, you can directly convert a set of raw scores into Stanine scores. Simply arrange the raw scores from the highest to lowest, and with the percentage of scores in each Stanine, you can directly assign the appropriate Stanine score in each row score. So let's take a look at the figure 8.10. So it is the normal, standard, and the standard scores. So we are done with the measures of position and the standard score. The next is the measure of covariability will be tackled by the next reporter.
So, good evening everyone. Today we will explore the concept of covariability and correlation, focusing on how to measure and interpret the relationship between two variables. Covariability refers to the extent to which two or more variables change together. A high degree of covariability suggests a strong relationship, but it doesn't imply causation. We'll use correlation to quantify the strength and direction of this relationship. Strength and direction of relationship between two variables are measured using correlation coefficient, denoted as R. The coefficient ranges from negative 0.0 to positive 0.0. An R of positive 0.0 indicates perfect positive correlation, and an R of negative 0.0 represents a perfect negative correlation. An R of 0.0 indicates no linear correlation. Real-world data rarely shows perfect correlation. Values close to positive 0.0 or negative 0.0 indicate strong relationship. Scatter plots provides a visual representation of the relationship between two variables. The positive correlation, negative correlation, and no correlation. The closer the points cluster to a straight line, the stronger the correlation. The Pearson product moment correlation is a common method to calculate R. This formula uses raw scores and mean scores to determine correlation coefficient. This method is suitable for datasets with interval or ratio level measurements. A simplified version of the Pearson product moment correlation uses raw scores directly. This formula is easier to use with a scientific calculator that can compute the necessary sums. Let's work through an example. We obtained a correlation coefficient of 0.705. This indicates a moderate positive correlation. To get a meaningful interpretation of the shared variance, you need to calculate their R-squared, the coefficient of determination. In this case, R-squared 0.705 squared is approximately 0.49, indicating that 49% of the variance in one variable is explained by the variance in the other variable. The remaining 51% is attributed to other factors. So this emphasizes that correlation doesn't equal causation. It's crucial to remember that correlation does not equal causation. A correlation simply indicates an association. It doesn't prove that one variable causes a change in the other. Always consider other potential variables and the content of your data.